If a set of events B1, B2, Bn forms a partition of the sample space, they are mutually exclusive and their union is the whole space. And each P of Bi is greater than 0, then for any event A we have P of A equals the sum from I equals 1 to n of P of a given Bi times P of Bi. Imagine rolling a fair 6-sided die. Let A be the event the outcome is even. Define a partition based on the first roll being 1 to 3, call this B1, or 4 to 6, call this B2. P of B1 equals 3/6 equals 1/2, P of B2 equals 1/2. Conditional on B1, the possible results are 1, 2, 3. The chance of an even number given B1 is P of a given B1 equals 1/3, only the 2 is even. Conditional on B2, the results are 4, 5, 6. Here P of a given B2 equals 2/3, 4 and 6 are even. P of A equals P of a given B1 times P of B1 plus P of a given B2 times P of B2 equals 1/3 times 1/2 plus 2/3 times 1/2 equals 1/6 plus 1/3 equals 1/2. Which matches the direct computation, 3 even faces out of 6. The proof relies only on the law of mutually exclusive events. A equals A intersect B1 union, A intersect B2 union ... union A intersect Bn, and summing their probabilities. Derivation : Bayes' theorem is a rearrangement of the total probability formula. P of A intersect B equals P of a given B times P of B equals P of B given A times P of A. Solve for P of B given A : P of B given A equals open parenthesis P of a given B times P of B close parenthesis divided by P of A. If open brace B sub I close brace is a partition, replace P of A with the total probability expression : P of B sub j given A equals open parenthesis P of a given B sub j times P of B sub j close parenthesis divided by sum over I of P of a given B sub I times P of B sub I. Medical test example: suppose a disease affects 1% of a population. A test is 99% sensitive, true positive rate, and 95% specific, true negative rate. Let D equals person has disease and not D equals no disease. P of D equals 0.01, P of not D equals 0.99. P of positive given D equals 0.99, P of positive given not D equals 0.05, 5% false positive. We want P of D given positive : P of D given positive equals open parenthesis 0.99 times 0.01 close parenthesis divided by open parenthesis 0.99 times 0.01 plus 0.05 times 0.99 close parenthesis equals 0.0099 divided by open parenthesis 0.0099 plus 0.0495 close parenthesis equals 0.1667. Thus, even with a very accurate test, a positive result means only about 16.7% chance of actually having the disease because the disease is rare. This inversion dash going from given disease to given test result dash is the core of Bayes' theorem. Problem setup: a factory produces widgets in 2 batches. Batch 1 supplies 40% of the total output and has a defect rate of 2%. Batch 2 supplies 60% and has a defect rate of 5%. Find the overall probability that a randomly chosen widget is defective. Solution using total probability. Define events. B1 widget comes from batch 1, probability of B1 equals 0.4. B2 widget comes from batch 2, probability of B2 equals 0.6. D widget is defective. Conditional probabilities. Probability of D given B1 equals 0.02. Probability of D given B2 equals 0.05. Apply the theorem. Probability of D equals probability of D given B1 times probability of B1 plus probability of D given B2 times probability of B2 equals 0.02 times 0.4 plus 0.0. 5 times 0.6 equals 0.008 plus 0.03 equals 0.038. So there is a 3.8% chance a random widget is defective. Why total probability helps? It lets us break a complicated overall chance into simpler pieces that are easier to measure, defect rates within each batch, and then stitch them together weighted by how often each piece occurs. Context: an email filter must decide whether an incoming message is spam. Historically, 20% of all emails are spam. The filter looks for the word free. Among spam emails, 70% contain free. Among legitimate emails, only 10% contain the word. Given that an email contains free, compute the probability it is spam. Inverse problem. This is a classic Bayes-type classification. Define events: S: email is spam, P of S equals 0.2. Not S: not spam, P of not S equals 0.8. F: word free appears. Conditional probabilities: P of F given S equals 0.7. P of F given not S equals 0.1. Apply Bayes: P of S given F equals P of F given S times P of S divided by P of F given S times P of S plus P of F given not S times P of not S equals 0.7 times 0.2 divided by 0.7 times 0.2 plus 0.1 times 0.8 equals 0.14 divided by 0.14 plus 0.08 equals 0.14 divided by 0.22, approximately 0.6. All 3 is 6. Thus, an email that contains free has about 64% chance of being spam. The filter can set a threshold. For example, label as spam if p greater than 0.5 and make a decision. Bayes' theorem provides the mathematically optimal way to update prior belief, 20% spam, with new evidence presence of a keyword. Scenario: suppose we have 3 mutually exclusive ways a machine can fail. Overload O, wear out W, or power surge P. These events form a partition of the failure space. O union W union P equals omega, and they never happen together. Their prior probabilities are P of O equals 0.3, P of W equals 0.5, P of P equals 0.2. We are interested in the event A. The failure was detected by a temperature sensor. P of a given O equals 0.9, overload quickly raises temperature. P of a given W equals 0.4, wear out may cause mild heat. P of a given P equals 0.2, power surge often bypasses the sensor. P of a equals 0.9 times 0.3 plus 0.4 times, 0.5 plus 0.2 times, 0.2 equals 0.27 plus 0.20 plus 0.04 equals 0.51. So there is a 51% chance the sensor will flag any failure. P of O given a equals open parentheses 0.9 times 0.3 close parentheses divided by 0.51 equals 0.27 divided by 0.51, approximately 0.529. The multi-event partition shows how the theorem scales beyond 2 cases. Just add more terms, each weighted by its own prior and conditional probability. A component in a satellite has 2 possible modes: new 70% of the time and aged 30%. The reliability probability of working for the next mission is 0.99 for a new component and 0.90 for an aged one. After the mission, the component is observed to have worked. Compute the posterior probability that it was new. Debs. Define events: n equals new, a equals aged, w equals worked. Priors: P of n equals 0.7, P of a equals 0.3. Likelihoods: P of w given n equals 0.99, P of w given a equals 0.90. Total probability for working: P of w equals 0.99 times 0.7 plus 0.9, 0 times 0.3 equals 0.693 plus 0.27 equals 0.963. Apply Bayes for P of n given w. P of n given w equals the fraction of 0.99 times 0.7 over 0.963 equals the fraction of 0.693 over 0.963, approximately equals 0.720. Interpretation: even though the component worked, the chance it was new is only about 72%, not 70%, because new parts are slightly more likely to survive. This numerical computation illustrates how Bayes updates belief after observing data, a technique frequently used in reliability engineering and fault diagnosis. Explanation: sample past paper questions. 1 JEE-Advanced 2018 Question 45. A factory produces items from 3 machines with probabilities 0.2, 0.5, 0.3. The defect rates are 1%, 2%, and 4% respectively. Find the overall defect probability and the probability that an item came from the second machine given that it is defective. Solution: apply total probability for overall defect, then Bayes for the conditional part. 2. Gate 2021 ME. A disease occurs in 0.5% of a population. A test has sensitivity 98% and specificity 97%. Compute the probability that a person who tested positive actually has the disease. Solution: classic Bayes problem. Many students forget to include the false positive rate. 3. IIT-JEE 2019 Paper 2. An email filter classifies messages as spam if the probability computed by Bayes' theorem exceeds 0.6. Given prior spam rate 0.25 and word occurrence statistics, decide whether a message containing two particular words is spam. Solution: multiply likelihoods, apply Bayes, compare with threshold. These questions are popular because they test the ability to set up partitions, compute total probability, and then invert the relation using Bayes. Practicing them builds fluency for the exam. Tip: write down a clear table of events, priors, and conditional probabilities before plugging into formulas. This avoids missing a term. Typical mistakes. Skipping the partition condition, total probability works only when the B sub I events are mutually exclusive and cover the whole space. Students sometimes add overlapping events, leading to probabilities greater than 1. Mixing up P of a given B and P of B given A in Bayes, the numerator uses the likelihood P of a given B. Flipping them gives the wrong answer. Forgetting the denominator in Bayes, some write P of B given A equals P of a given B times P of B and stop there. The denominator P of A equals the sum of P of a given B sub I times P of B sub I is essential, especially when there are several hypotheses. Using percentages directly, treat 30% as 0.3, not 30, otherwise the result explodes. Shortcut: when you have only two hypotheses H and H bar. Bayes can be written as odds after data equals odds before data times the likelihood of data under H divided by the likelihood under H bar. This odds form lets you multiply rather than compute a full denominator each time, saving time in exams. Trap in conditional probability trees, forgetting to multiply by the branch probability when moving down the tree. Always write the product of the path probabilities before summing. Quick checklist for exams. Verify that the events form a partition. List priors P of B sub I and likelihoods P of a given B sub I. Compute P of A with total probability. Plug into Bayes, numerator equals likelihood times prior, denominator equals P of A. Keep an eye on decimal versus percentage. Following this routine eliminates most common errors and speeds up calculation.